Okay, so this is exercise 5H. We're talking about exponential growth and decay. Okay, the rule that we use nearly all of the time is if A is the quantity that we're looking at any time t, we define our variables, then A equals A0 e to the kt. Now A0 represents the initial value, that is when time equals 0. T represents time, K is the rate constant. What does that tell us? Well, if we're looking here, if K is greater than 1, then that means that our graph is going to have exponential growth over time. If K is less than 1, then we're going to have exponential decay. So things are going to get smaller, and this is time along the x-axis. Okay, here's our problem. The population of a town was 8,000 at the beginning of 1992 and 15,000 at the end of 1999. Assume that the growth is exponential. Find the population at the end of 2001, and then it says in what year will the population be double that of 1999. So how do we start this? We define our variables. Let P be the population at the time t years. Then we substitute that into our exponential equation. P equals the initial value of P, e to the kt. Our first job is to find K. What is K? So we're going to substitute in. It tells us that the initial value, 8,000 at the beginning of 1992. So we'll say 1992 means time equals 0. The initial population is 8,000. So we substitute that 8,000 into the equation. So the population at any time is 8,000 e to the kt. Now we're going to use the other piece of information, 15,000 at the end of 1999. So at the end of 1999, that's time equals 8 and P equals 15,000. So our equation becomes 15,000 equals 8,000 e to the power of 8k. Now our job is to solve for k. So divide 15,000 by 8,000. The zeros can cancel out. We're going to use our logarithms now. So we've gone up here. Just continue on. Use our logarithms now to get k by itself. So k equals 1 on 8 log e to the 15 on 8. In a calculator-free situation, that's our answer. If we do have a calculator, we can approximate that as 0.0799. So now we're ready to answer the question. It says find the population at the end of 2001. So we count 2001 is time equals 10. Substitute that 10 into the time, and using k equals 0.079, that gives us an answer of 17,550. Now here's part B. B. Bit of trouble with the B. For the population to double, we're looking for population to be equal to 3,000. So we're going to substitute 3,000 into our equation. We know what k is. We're trying to find t. So 3,000 over 8,000. That becomes 15 over 4. Logarithms, use logarithms to get kt on by itself. Substitute, get t by itself. Then we substitute our values in. T equals 16.73 using our calculator. So the population will double in the 17th year. Okay, let's do another one. Temperature in a kiln, this is a bit more complicated. Temperature in a kiln is modelled by the equation T equals T naught. So they've given us the equation here, e to the kt. T is time to reach temperature, capital T, in degrees Celsius. If the temperature is 450 degrees Celsius after 15 minutes and 250 degrees Celsius after 1 hour of cooling, find the initial temperature inside the kiln, the temperature after 2 hours, the temperature taken for the kiln to reach 150 degrees. So this is a situation we're trying to find the initial temperature first. T, there's our equation. The first piece of information tells us when time equals 15. That's 15 minutes. T equals 450. I'm going to convert, notice I convert my 15 minutes into 1/4 of an hour. So I'm going to have time in hours. So 450 equals the initial temperature, E to the 1/4 K. When time equals 60, again that's 60 minutes. This is, temperature equals 250. Again, I'm going to convert that and I'm going to say, well, that equals 1. The 60 equals 1 hour. So 250 equals the initial temperature, E to the 1K. I now have two equations with two unknowns. I'm going to use simultaneous equations, divide one equation by the other. The initial temperatures cancel out. I'm left with 5/9 equals E to the 0.75 T. Now I can just use logarithms to solve. So I get a calculator free answer, hit the calculator and get negative 0.784. Substitute that back into the equation to get the initial temperature of 547.4 degrees Celsius. Now using that information, I'm going to temperature after 2 hours of cooling. Well, I've substituted the values in. When time equals 2, I substitute that in and I come out with 114 degrees 0.1 Celsius. And the time taken for the temperature to reach 150. This time I still have my initial, my P0 initial temperature, and I've got the same K. And this time I want when is the temperature going to equal 150. So we substitute that in for temperature. And you can solve that directly on your calculator. And that will tell you that the temperature is, it takes 1.65. Now, we don't like 0.651 hours when you wouldn't say I'm going to meet you in 0.651 of an hour. So you need to convert that into minutes. So that's 1 hour and 39 minutes for it to take to reach the temperature of 150 degrees.